Welcome back, boys and girls. We are still doing our metric revision, where we are putting together the concepts which we have explained previously and try and see how we can apply them in typical examination questions. So in the last session we tackled all the questions involving organic molecules or organic chemistry. So in this next session we want to try and see if we can explain we can apply rates of reactions and also carry out a detailed study of the industrial processes and quickly look at electrochemistry, and from there we'll wrap up our study of our revision of these typical examination past questions. So I'm going to move a little bit faster so that we can cover as much as we can. So if you take a look at this next question here, it's going to talk about rates of reaction. So you say learners use the reaction of a sodium thiosulfate solution with dilute hydrochloric acid to investigate several factors that affect the rate of a chemical reaction. And then the balanced equation of the reaction is given below. So let's take a closer look at the balanced equation. This is the sodium thiosulfate plus hydrochloric acid to give us sodium chloride plus sulfur dioxide plus sulfur as solid plus water and liquid. So define reaction rate. What exactly would we say is the rate of a reaction? Remember, every time we are talking about rate, we are talking about something happening per unit time, meaning that it's a measure of the speed at which the reaction is taking place. Okay, so just for 2 marks, you put it in simple terms. We are saying that a rate of a reaction rate is a measure of the speed at which a reaction is taking place. Okay, so we've got 3 investigations carried out here, 1, 2, and 3. So in the investigation 1, here are the results, and as you can see, we've got a graph of the reaction rate versus the concentration of sodium thiosulfate. So if we study this data which has been presented graphically, you can actually see that this is telling you about the rate of reaction and the concentration. So you can see that as the concentration increases, the rate of reaction is directly proportionally increasing also, because when we had a lower concentration, the rate was very slow, but when we had the highest concentration, we also had the highest rate of reaction. So we can conclude from the study of this diagram that the higher the concentration, the higher the rate of reaction. So let's answer the questions that follow. So I said for this investigation, write down the dependent variable. So the dependent variable is the rate of reaction. And what does it depends on? It depends on the concentration. So write down the conclusion that can be drawn from the results. We have just said it from our study of the diagram. That the higher, so you can conclude that the higher the concentration, and then the higher the rate of the reaction for 2 marks. Just that. Okay, look at the investigation number 2. They are saying that the Maxwell-Boltzmann distribution curves A and B below represent the number of particles against kinetic energy for the reaction at 2 different temperatures. Okay. So here we are saying these are the number of particles and the kinetic energy. So you can look at this that for this curve A, you see we've got a point where we've got the high number of particles very high, and then their kinetic energy is very low, and then they do follow like that. While for reaction B, and then we know what's happening at P. And we understand that at P, it is a measure of the activation energy, the minimum amount of energy required to set the molecules into a reaction. So the question is asking, number 1, what does line P represent? We are saying it represents the minimum amount of energy required for the molecules to react. Okay. We're saying which curve A or B was obtained at the higher temperature. So you can see what is happening here. That with curve A, if the kinetic of the A is taking place very fast, it means that A is at a higher temperature than at B. Okay, so A was obtained at a higher temperature than B. So explain in terms of the collision theory how an increase in temperature influences the rate of the reaction. Boys and girls, if you look at this is 4 marks. So for 4 marks, that means you should present a very strong argument that will convince the explanations attached here what exactly is happening with temperature as a factor that influences the rate of reaction. So I'm going to go into the fine details of these explanations and see if we are going to put down something that will amount to 4 marks. So we are saying that in terms of the collision theory, we are saying an increase in temperature, we know that every 10-degree rise in temperature, the rate of the reaction doubles. And then when it doubles, what it means is that the molecules are now reacting twice as fast as they were doing. But how does that happen? So we are saying, according to the collision theory, the molecules, they move around and bump against each other and bump against the walls of the container. And it is during those random movement and collisions where they bond and form molecules and then form intermediates, which will go on to form products of the reaction. So we are saying an increase in temperature increases the kinetic energy of the molecules. What is kinetic energy? It is the energy we use to make molecules move around. So the more energy they have, the more random and the faster they move around. So what does that have to do with temperature? We are saying when you are increasing temperature, you are increasing heat. And the heat is absorbed by the molecules and use the heat as kinetic energy, and the kinetic energy will increase the random movement and collisions of molecules and increase the rate of the reaction. Okay, for 4 marks, that's what you're supposed to say. So in investigation 3, look what is happening here. We are saying that the potential energy diagrams X and Y below represent the reaction under 2 different conditions. So let's study these reactions and see what is happening here. So this is potential energy and the reaction coordinate. So if you look at this, it means that if these are reactants, and then they will need to have a high potential energy, and then when they react, they form the products at a lower temperature like that. And the scheme Y shows that the molecules, they need some energy but not as much, and they will still produce the same product. So what is happening here? Before we even go any further, we can conclude that this is the same reaction, starting with the same reactants, giving us the same products, but something is changing here. And what is actually changing here are one or two factors that are affecting the rate of a reaction. So by randomly applying your knowledge here, you might conclude by saying this could be a catalyzed reaction, where the catalyst is used to lower the activation energy required to drive the reaction, while this one is an uncatalyzed reaction where you have to supply as much energy to drive the reaction to produce the same product of the reaction. So let's see what the question is talking about. So they are saying, give a reason why curve Y differs from curve X. I've just explained it. That Y has got a lower energy but it is undergoing the very same reaction to give us the same product. And this we can say that this is happening at a lower temperature, while X is happening at a higher temperature. Okay, so they say in one of the investigations, 100 cubic centimeters of 0.2 moles per dm cubed of hydrochloric acid in aqueous solution reacts with excess sodium thiosulfate, and the solution is then filtered. After filtration of the solution, 0.18 grams of sulfur is obtained. Calculate a percentage yield of sulfur. Boys and girls, this is a tricky question, but your understanding of stoichiometry, especially with specific reference to this balanced equation, it should not give you any problems. What is happening, where and how. So what I'm going to do, I'm going to narrow down this equation, because the parameters we have here, which we need to consider, is the volume, 100 cubic centimeters, and we are saying the limiting reagent here is hydrochloric acid, and our thiosulfate is in excess, so its concentration is not going to affect how things are going to take place here. So I'm going to use three parameters, boys and girls: the volume of the hydrochloric acid, its concentration, and the amount of sulfur we are going to obtain. So if I'm to cut down this reaction, I'm going to have it like this. Let's bring it here. I'm going to ignore everything else and just take that 2 hydrochloric acid molecules are going to give us 1 sulfur molecule. So here we are. We are saying 2 HCl in aqueous solution is the proportion here is that it's going to give us 1 sulfur solid. So the ratio of this reaction is 2 to 1, like that. So let's see what's happening here. So let's interpret the data as we are given. So we are saying that we have got 100 mils of 0.02. Ooh. 0.2, sorry. There we are. So it's going to be 0.2 moles per dm cubed. And then we are going to produce 0.18. So it's going to be 0.18 grams of sulfur. So here's the $1 million question. Is saying calculate the percentage yield of sulfur. Okay. So we are saying from this reaction, let's see if the ratio is 2:1, and so how many moles of sulfur are we producing from this whole reaction? So we know that number of moles or concentration is equal to number of moles over volume, right? But for us to find the number of moles, we are going to say number of moles is equal to concentration times volume. Okay. So if we change 100 mils to number of moles, to dm cubed or liters, it's going to give us 0.1 dm cubed. So if we say number of moles is equal to concentration times volume, it's going to be 0.2 moles per dm cubed times the volume, which is 0.1 dm cubed. So this and this, they cancel each other. 0.2 times 0.1, it will give you 0.02 moles. Okay. So these are the number of moles of sulfur solid produced. Okay. So from there, we want to figure out that how much of the sulfur do we have. We are already told that we have got 0.18 grams of sulfur. So if this is 0.18 grams of sulfur, for us to determine the percentage yield, we need to find out that how much of sulfur was there initially, and then we can relate it. So we are saying the relative molecular mass of sodium thiosulfate. Let's calculate it together, boys and girls. The relative molecular mass of sodium thiosulfate. So we are saying this is going to be Na2S2O3, like that. Sodium is 23 times 2 is 46. Sulfur is 32 times 2 is 64. Oxygen is 16 times 3, that's 48. So this will give us a total relative molecular mass of 10 plus 8 is 18, 8 1, 10, 4, 5, 158 grams. Okay. So I'm saying that in 1 mole of sodium thiosulfate, it is in the excess of it reacting with 2 moles of hydrochloric acid, and it's giving us a 0.18 grams of sulfur. So for us to determine percentage yield of sulfur, boys and girls, we know that we need to know the mass we have over the initial mass, and then we multiply it by 100. Okay. So how many marks there? For 6 marks. So if you put in the values and then you calculate, I don't have a calculator with me, but if you just put in the values of 0.18 over the relative molecular mass of thiosulfate and then times the number of moles there, we obtain 0.02 times 100. It will give you the percentage yield of sulfur. Okay. So moving a little bit faster, let's quickly go on to question 6, which is going to talk about fertilizers or industrial processes. So you see that we've got the balanced equation represented as follows. We've got nitrogen reacting with hydrogen to give us ammonia gas. That's the Haber process. So in industry, the product is removed as quickly as it forms. There's a reason why that happens. So they are saying write down the meaning of the double arrow used in the equation above. So you see we've got an arrow moving forward and an arrow moving backward, meaning that this reaction is reversible. And as much as nitrogen and hydrogen combine to form ammonia, ammonia also breaks down to form nitrogen and hydrogen gases respectively, just for 1 mark. Give one reason why ammonia is removed from the reaction vessel as quickly as it forms. So you see that the primary reason is when this reaction is reversible like this, it means that a point in time will be reached when the forward reaction is equal to the reverse reaction, meaning that the reaction reaches what we call equilibrium. So if we keep on removing the ammonia as quickly as it forms, it means that we prevent this reaction from reaching equilibrium. So when it does not reach equilibrium, it means that the reaction will keep on moving in the forward direction. In the forward direction is the formation of ammonia, which is our target product. We are not targeting keeping reactants, we are targeting forming products. So whatever little products we have, before the reaction establishes an equilibrium, we tape out the ammonia, so the reactants will keep on reacting in the forward direction. This one, boys and girls. Okay. So the graph below shows the percentage yield of ammonia at different temperatures and pressures. Okay. So here is the graph of percentage yield of ammonia versus pressure. So this is the percentage yield of ammonia and this is the pressure. So you can see at 350 degrees Celsius, if you increase the pressure, the percentage yield is increasing rapidly. But as you increase the temperature to 450, it becomes lower and lower. So what does this tell you? Before you can even go into the question, we can tell you that you can see that temperature is having an influence on this reaction, such that the more you increase the temperature, the reaction favors the reverse reaction. So what does that imply? It implies that there is an exothermic and endothermic interpretation you are supposed to attach here. So let's see what's happening. Write down the percentage yield of ammonia at a temperature of 450 degrees and a pressure of 200 atmospheres. So you just go and attach to 200 degrees here, and then if you go up with it, you'll see that the percentage yield at 400 degrees Celsius is 20%. That's 400 points else. And then the next part is very interesting. They are saying, refer to Leach-Taylor's principle to explain each of the following deductions made from the graph. So the million-dollar question is, what does Leach-Taylor's principle say? To remind you, boys and girls, we are saying Leach-Taylor's principle says that the reaction at equilibrium will respond to counter the change of the conditions and how the reaction is taking place. So that, for example, if a reaction is endothermic, if it is endothermic, it means that if you reduce the temperature, the reactants are more favored, so the products are going to break down to form the products, the reactants, and then they will break down until a new equilibrium is established. But if it is, if you increase the temperature, it means the reaction will favor the forward reaction. So the formation of the products is going to increase until a new equilibrium is established. Let's say it is the concentration. If the concentration of the reactants is increased, it means that the increase in concentration will favor the forward reaction where products are formed. And that will take place until an equilibrium is established, and then we'll be having the concentrations remaining constant. So now let's say, for example, you remove the products as they are immediately produced. So that means the equilibrium is going to shift such that more reactants are going to combine to form the product, so that until a new equilibrium is established. That's what Leach-Taylor's principle says. So here we are saying that for a given pressure, meaning that pressure is constant, the yield of ammonia at 500 degrees Celsius is much lower than that at 350 degrees Celsius. So here we are. We can randomly pick up at any pressure here. So we are saying at any given pressure, the amount of ammonia at 500 degrees is lower than that of ammonia at 350 degrees. So according to Leach-Taylor's principle, we are saying that this difference in a percentage yield tells us that this balanced reaction here is an exothermic reaction. It gives out energy. So if you increase the temperature, the reaction favors the reverse reaction, where the products break down to form reactants. But at a lower temperature of 350, the reaction favors the forward reaction, where the reactants combine to form the product. So according to Leach-Taylor's principle, we are saying the yield of ammonia at 500 degrees Celsius is much lower than that at 350 degrees, because the products will have to break down to consume the excess energy that is being supplied to form products which are more thermodynamically stable than the products. Okay. So for a given temperature, the yield of ammonia at 350 degrees atmospheres at 350 atmospheres is much higher than that at 150 atmospheres at any given temperature. So let's take a random look at what happens at 350 and at 150. So here we are. This is 150 and this is 350. So we are saying at any given time, the concentration, the percentage yield of this is higher than the percentage yield of that. So it's for obvious reasons, isn't it? That the higher the pressure, you increase collisions between the gaseous reactants. So remember, our balanced equation is showing us that the reactants are gaseous molecules, and if you do molecular count, here you've got 4 molecules of gases, while this side you've got 2 molecules. So if you increase the pressure, it means that you need to reduce the amount of molecules so that you balance and you bring the system into equilibrium. So it will favor the combination of reactants so that you form fewer molecules of ammonia, and then you establish an equilibrium like that. Okay, so that's for 2 marks. Get to that a technician prepares ammonia by reacting 6 moles of hydrogen and 6 moles of nitrogen. Calculate the maximum number of moles of ammonia that can be obtained in this reaction. Boys and girls, if we look at our balanced equation here, if you look at our balanced equation, you will see that they react in the ratio of 1:3. Okay, so if they react in the ratio of 1:3, this question is telling us we've got 6 moles of hydrogen and 6 moles of nitrogen. So look at this, we're saying under ordinary conditions, nitrogen reacts with hydrogen to give us 2NH3 gas. So we are saying the ratio here is 1:3 to give us 2 of these. But now if you bring 6 nitrogens and 6 hydrogens, what it simply means here is that you are going to have we are going to use all the hydrogen, 6 moles of them, but from this side you are only going to make use of 2 moles. So we are going to have an excess of 4 moles are going to remain unreacted. Okay, so meaning that if you use 2 moles of nitrogen, you are going to have 4 moles of NH3 here, since this ratio is 1:2. So if here you've used the 2, here you are going to have 4 of them forming. So here we are saying, to answer this question, they are saying calculate the maximum number of moles of ammonia that can be obtained in this reaction. So the maximum number of moles is just what? 4 moles of ammonia, because our limiting reagent is hydrogen, and as soon as you make use of all the hydrogens, the other nitrogen is going to remain unreacted, and it will only produce 4 moles of ammonia. The above reaction now takes place in a 500 cubic centimeter container at a temperature of 350 degrees Celsius and a pressure of 150 atmospheres. And then the system is allowed to reach equilibrium. Let's see what was happening here earlier on. So you are told that balanced equation of this, we are not initially told it in what volume was it taking place, but we know that things were happening at these respective pressures and temperatures. Okay, so now here we are told that the reaction is taking place at 500 degrees in a volume of 500 cubic centimeters at a temperature of 350 degrees. So use the graph above and calculate the equilibrium constant Kc for this reaction under these conditions. Okay, so this is for 7 marks. Boys and girls, you really need to know how to relate what is happening here. So we know that if you are given all these conditions, 500 cubic centimeters container, with a temperature of 350 degrees and a pressure of 150 atmospheres. Let's see here what has been happening. So you can actually see that this is 350 degrees Celsius and at 150 atmospheres, there we are 150. We had a percentage yield of 35%, and we are saying this percentage yield tells us how much of the ammonia which was produced. So you will see that for you to carry out a simple calculation or the KC, we can easily find it by drawing a tangent at this point, like that, and then if you calculate the gradient of this, then you compare with the quantities of the ammonia produced under these conditions, and then you can convert all those to concentrations. And how do you determine those concentrations? By simply comparing the number of moles you are obtaining from that deduction to the volume you have there, because we know that concentration is equal to number of moles over volume. So you are given the volume, and then you are going to use your deduction here of the percentage yield to determine the number of moles of ammonia you are going to produce, and then you express that in terms of the equilibrium expression, and you determine your KC. So here we are told that define a base in terms of the Arrhenius theory. We know that according to Arrhenius, Arrhenius says that a material can exhibit acidic or basic properties only when it is dissolved in water. So we are saying that according to Arrhenius, a base is a substance that increases the concentration of OH minus in aqueous solution. For 2 marks. Explain how a weak base differs from a strong base. So a weak base, it does have the OH in its molecule, but does not readily give them away or release them or dissociate to give away the OH minus. While a strong base is one which quickly or easily gives away the OH from its molecule. And what makes them different is that the Kb value for a weak base is very, very small, while a Kb value for a strong base is very, very high. Okay. So if you write down the balanced equation for the hydrolysis of sodium hydrogen carbonate hydrolysis, we are saying this is sodium hydrogen carbonate. If you react it with water, we are going to have sodium hydroxide plus H2CO3, like that. So you just need to check your standard conditions. So if this is a solid and this is a liquid, so this is aqueous and this is aqueous, like that. Okay, right. That's for how many marks? That's for 3 marks. Okay. The learner wishes to identify element X in the hydrogen carbonate. Okay. And then to do this, she dissolves 0.4 grams of XHCO3 in 100 cubic centimeters of water, and then she titrates all of this solution with a 0.2 mole cubed hydrochloric acid solution. And methyl orange is used as an indicator during the titration. So calculate the pH of the hydrochloric acid present. Boys and girls, we know that pH is always equal to minus log the concentration of H plus, like this. So if you look at this information, we are told that we've got 0.2 moles per dm cubed of hydrochloric acid. Okay. So we know that hydrochloric acid breaks down to give us H plus Cl minus. So if the concentration is 0.2 molar of HCl, it also produces 0.2 molar of H plus. So meaning that the concentration of H plus is going to be 0.2, so it's going to be minus log the 0.2. Those who have got calculators, if you punch this in your calculator, I think you see that this is going to be equal to 2, pH of 2. Okay. Then the next part is saying that give a reason why methyl orange is a suitable indicator in this titration, because we are saying that with hydrochloric acid, the methyl orange changes from a light orange color to is it purple. It's going to be colorless, so it will disappear completely, and then you'll know that you have reached the end point. Okay. And then at the end point, she finds that 20 cubic centimeters of the acid neutralize all the hydrogen carbonate solution. So the balanced equation for the reaction is XHCO3 plus HCl minus HCl plus it will give us X of the chloride plus carbon dioxide plus water. So identify element X by means of a calculation. So how do we do that? We will carry out all the necessary, with the determinations using our volumes we have there, and see that if they are reacting in these proportions, and compare it to the one which involves different salts, like here we wrote down the balanced equation for the hydrolysis of sodium hydrogen carbonate. So what you will see in the essence of time is that you have to determine the concentration of this. If you've got 0.4 grams of XHCO3 in 100 cubic centimeters, you need to change this into a concentration. So if it is 0.4 grams of that into a concentration, we know that concentration is equal to number of moles per unit volume, and you are given grams, and we don't know what X is, but we've got the other part is hydrogen carbonate. So you need to revert back to this whole quantity. So, but what we know for now is that this is in 100 cubic centimeters of water. And then, so for that reason, if you check that at the end point, he finds that 20 cubic centimeters of the acid neutralizes all the hydrogen carbonate. So you need to change the number of moles. So we've got the concentration of the acid is 0.2, and then we've got the volume as 20 cubic centimeters. Change it to number of moles by simply saying you convert 20 cubic centimeters to dm cubed, and gives you 0.02. 0.02 times 0.2, it will give you 0.004. That's number of moles. And then when you compare this balanced equation, you see that 1 mole of this reacts with 1 mole of that to give you 1 mole of the X chloride plus 1 mole of that. And boys and girls, what I want you to remember is that you are already told that this is the balanced equation for the reaction. So the quantities you have here are telling you the molar ratio of this reaction. So this is 1 mole reacting with 1 mole to give you 1 mole, 1 mole, and 1 mole. Okay. So for us to understand what is happening here, you can actually see that for the HCO3, if we are to go back to this calculation, you can see that if you consider that COH3, this carries a charge of minus, meaning that whatever X is should be a compound, an atom in group 1. And we know in group 1, since this is not a hydrogen, we can start from lithium, sodium, all those other atoms in group 1. So X is most likely to be sodium, where it forms sodium carbonate like this. And that's what will only make sense since all this is one more. Boys and girls, in the interest of time, let me conclude here. Thank you very much. Okay.